All right, so this chapter is all about soaps and detergents. So this is how we clean up the waterways, clean up all of these wastes, clean up all of this stuff. So first of all, soap is one of the oldest man-made chemicals, and it is made from using sodium or potassium salt, so like sodium chloride or any of those types of salts. And basically we mix it with a fatty acid. So basically like when you cook and you have all the fat and grease left over, that's what people used to make soap with back in the day. This is called soapinification, and basically we heat up animal fat with a strong base like potassium hydroxide or sodium hydroxide, which is what lye is. Sodium hydroxide is lye. And they also used to use soda ash. Back in the day, basically they would take ash of organic material and they would just boil it down in water. And in the process it would make it slightly basic. And so then they would just add fatty acids or an animal fat of some sort to it. And this would break the bond and it would allow them to bond together. Okay, when I'm talking about fats, I'm actually talking about triglycerides, which a triglyceride is 3 chains of fat, which we see right here. 1 chain of fat, 2 chains of fat, 3 chains of fat, and then this over here is your glycerin. So we have a glycerin attached to 3 fats, so it's a triglycerol. Glycerin. So basically, we have our glycerin plus our 3 fatty acids. So when you put it in this basic solution that I was just talking about, whether it be potassium hydroxide or sodium hydroxide or the soda ash solution I was just telling you about, basically what happens is it breaks the bond between the glycerin and the 3 fatty acids. So now we have 3 fatty acids floating around with a positive end. Okay, we've talked about bonding, right? We've talked about ionic bonding. Positive and negatives attract, correct? And so basically, if you use a strong base, you will allow it to attach a sodium right here to the negative. If we remove the glycerin, it now has a negative charge. We can then stick a sodium onto it. And the reason that this is a good thing, because I don't know about you guys, but when you're thinking about animal fat, do you think, ooh, soap, it's going to clean everything and make it good? No, but that one little step really does make a difference, because basically what it does is it allows that fat to have a split personality. So usually does fat mix with water? When you're trying to clean your pots and pan, maybe you've made bacon or hamburger or whatever, and you're trying to clean, does it really work to just rinse it off the pan? No, actually it probably makes it stick to the pan even more because the water's cold and the pan is a little bit warm, correct? Well, but if you add soap, what actually ends up happening is now we have 2 parts to this. We have a hydrocarbon tail, which is non-polar. Does everybody remember what polar means? What does polar mean? You have opposite charged ends, right? We have 2 poles. One is positive, one is negative. Okay? So the hydrocarbon tail is non-polar, which means it doesn't like water. Water is polar, which means it has charges. Okay? We like to call this hydrophobic. Phobic, phobia. Hydrophobic means it doesn't like water. Okay? The other end, like we're going to call head, and I'm going to draw you a picture in just a second. This end likes water, so it's called hydrophilic. So our soap molecule that we just talked about, the fatty end, we attached a sodium to it now, right? So we have a soap salt, if you want to call it, for lack of a better words. When you put the soap in the water, the tails want to get away, and the heads like the water. So basically, we draw a picture. So we have a soap, and we have 2. Okay, and over here we have our grease, right, that you're trying to get off your pans. So basically, when you add soap, what ends up happening is, here's our grease. And so when we're trying to get our grease to go away, our hydrophobic ends stick to the grease, and the hydrophilic end goes to the outside. And it just continues to coat this grease like this, like you guys can see there. Because all of these guys are hydrophobic, they don't like water, so they're trying to get as far away from water as possible. And since this guy is also hydrophobic, they're best friends. We don't like the water, let's stick together. These guys are hydrophilic, which means they like water, and since water is out here because you're trying to wash your pan, they are going to arrange themselves to be close to the water because they like water. So now basically what happens is we have made this soluble in water because now the outside likes water. And that's why when you use soap, it then rinses all the grease off of your pan. Okay? These things that I just drew on the board that are also up here on the slide, this is actually something called a missile. And these are round spheres. And basically all of your grease and dirt that you don't want goes in the center, and then it's allowed to be washed away now by the water. Okay, these missiles that I just practiced drawing on the board do not dissolve in water. So if you guys ever notice that when you put soap in the water, do you notice that sometimes before it suds up, it just kind of floats in the middle? You get little circles of soap? Because it doesn't dissolve in water. It just kind of floats in the water. It's like suspended in the water. It doesn't dissolve in it. You can still see where it's at. All they do is they honestly trap the non-polar materials in the center, and then that allows it to be carried away by the water and washed down the sink. You guys like my picture? Okay, well, soaps aren't the best. The soap we use in our kitchen sink, do we put that in our washing machine? No, because does soap always work? Does one soap always create it equal? No, we have different types, and the reason that not all soaps work is because soaps do not work well in acidic conditions, and water is slightly acidic. Normal water is always slightly acidic, and then we add things to our water, so on and so forth. We have acid rain, we have all these other things that make it even more slightly acidic. So basically what happens when you put a soap in an acidic condition, it turns it back into a fatty acid. It breaks that bond between the sodium and the fat, and it turns it back into a fatty acid, which we don't want because that's not going to help us clean anything, right? And so basically what happens is the hard water, which is what we have around here, our hard water contains calcium, magnesium, and iron, and we call these hard ions. And this is what is found like on your shower head. You can see the white stuff, right? When you boil water in a pan, if you let it boil off, you'll get the white stuff left behind. These are all of the ions that are found in your water. Basically what happens is these compete with the sodium and the potassium salts that are attached to make our soap. These compete with these ions, and sometimes they will replace them. But when they replace them, they no longer make a soap. They kind of make an in-between. It's not a fatty acid, and it's not a soap. And this is what you guys see at the bottom of your bathtub that makes the bathtub ring. Because we have hard water. Unless you have a water softener in your house. That's why we have the soap scum in the bottom of the tubs and in the sinks and stuff. So, if we used rainwater or distilled water, we would not have a problem at all. We would not have this scummy precipitate finding. Soap would be perfect and everything would be good. But that's not how the real world works. We use water from lakes, rivers, and wells. And in order for water to get in lakes, rivers, and wells, it goes over the ground. And in the process, it picks up all of these ions like calcium, magnesium that we see in our water buildup. This leads to hard water. And there are two types of hard water. We have something called temporary hardness. This is reactions that form magnesium and iron, but they do not form from carbonate reactions. These are really easy to get rid of. Does everybody know what carbonate is? Calcium carbonate, limestone. So do we have these types of ions around here? No, because we have these types. Because we have, our bedrock is calcium carbonate. And so we're going to have the permanent hardness ones like calcium, magnesium, and iron that are all found in the breakdown of carbonate. Okay? The first ones are a little bit easier to get rid of. The second ones are a little bit harder to get rid of, but they're not temporary and they're not permanent. Okay, those are misleading words. They're just trying to give you a different level of how hard it is to get rid of them. Okay, so how can we fix this problem? Hard water breaks apart our soaps. How in the world can we fix this problem? Well, first of all, we can just boil the water away. If we have temporary hardness, which means non-carbonate issues, basically it converts the bicarbonates back into their carbonates. So basically it reverses the reaction. They're no longer in the water anymore, and then we don't have to worry about our soaps being broken down. This is what is responsible for the scale buildup in your coffee makers, because what happens in your coffee makers? Put the water in there, it boils, and that's why you get all that condensation at the top where the water starts coming out, is because we're getting rid of these temporary hardness ions. The precipitation, these type of solution, basically what we can do is we can precipitate or remove both temporary and permanent ions. And basically we can put sodium carbonate, which is also called a washing soda, in our solution, and it bonds with the ions in the water and causes them to precipitate into solids at the bottom of our solution. So there are two different ways here. Another way that we can fix our hardness solution is something called an ion exchange, and this is actually what a water softener does. Basically what happens, if you have a water softener in your house, you run your hard water through it, and as you do that, it exchanges the soft ions for hard ions when it passes through it. So it's just kind of like causing a chemical reaction, and it's taking all the ions we don't want out and putting ions that are okay, that aren't going to affect. So remember, some of them were okay and they didn't affect, some of them were bad. When it no longer works, because water softeners, eventually you're going to run out of ions to replace it with, a lot of times you can just add a saltwater solution to it, and it kicks out all of the hard water ions that we were trying to get rid of. It causes them to be flushed out, and it kind of resets everything. So a lot of water softeners do this manually once a week, once a month, in the middle of the night, because most people aren't using their water in the middle of the night. Because basically what it's going to do is it's going to kick out a whole bunch of the hard water ions we're trying to get rid of all at one time. And so you wouldn't want to be doing that when you're taking a shower or trying to do the dishes or something like that. Another type of ion exchange is a cation exchange and anion exchange. Basically, these are just more specific forms of this. A cation exchange is we're trying to replace whatever the positive ion is with hydrogen, because then it will form water. Anion exchanges are trying to replace whatever your anion is with oxygen or hydroxide. And in that way, you're again producing water. Because if we have hydrogen, one H and one OH, that's going to make H2O. So it's basically just allowing us to make purer water. But this still doesn't solve the problem, because we have to use water softeners. Okay, so they've actually developed a better soap, and we call them detergents. Okay. Detergents are usually made out of synthetic compounds, and they are derived from petroleum, and they are less affected by hard ions. Okay, so if you remember the picture I just drew up here of soap, basically the soap had a really long end, like a tail, right? And then over here it had a sodium ion, which we like to call the head, right? So it had the tail. This is positively charged, this end was neutral, right? And so it attracted to water. Detergents honestly work the exact same way, but instead of having a sodium on one end, they have a benzene ring on the other end. That's what you see right here. Okay. Now, there are two types of detergents. We're going to talk about those in just a second. But basically, these produce something called a surfactant, which is a synthetic soap. They work the same way. They have a hydrophobic and a hydrophilic end. However, this time around, they are not precipitated by hard ions, so our hard water around here is not going to affect them, which is why they work better when you are doing laundry. That's why we use laundry detergent and not laundry soap. All right, so there are basically two types of surfactants. We have this one up here, which you can't see very well. We have this one, which is called the ABS detergent. This one is called the LAS detergent. The big difference between these two is this one is a long chain, and this one has these branched items coming off of it. Do you guys see the difference between these two molecules? Okay, the branched chain, basically each one of these points that you see is a carbon molecule with some hydrogens attached to it. So instead of writing 12 hydrogen carbons, they just kind of wrote a shorthand for it. These produce lots and lots and lots of suds. They are not very biodegradable. So when we first started coming up with this type of detergent, it accumulated in the waterways. And so as you were watching like runoff, you would see runoff sudding up because it was really hard for our ecosystem to get rid of it. And that was this one. And the reason it was so hard is because we had these branched things hanging down. So it wasn't, fatty acids are naturally occurring, so it would be easier for us to break down those. And if you compare this picture to this picture, isn't that chain a lot more similar? This long chain and this long chain. Yes, so it was a lot easier for our ecosystem to break it down. This one was changed in the 1960s, and honestly, this one just contains a linear hydrocarbon, which is what this chain is called. And this is just as good of a cleaner, except it produces fewer suds, and we can break it down in our environment just a little bit better. So they do the same things, it's just one is safer for the environment over the other one. Okay, well, usually when we have detergents, we do have a surfactant. This is the guy that's surrounding the dirt and the grease and washing it away, just like soaps did, except we usually need something else in the detergent. We also need something called a builder. This is a molecule that ties up your hard ions that we just said were bad. Well, hard ions don't affect detergents as well as bad as they do soaps, but if we have a lot of hard ions in there, it still will affect how well a detergent will work. And so we throw builders in there. They reduce the cleaning ability, but at the same time, they work better, and detergents work better in soft water, so it's kind of it does slow it down a little bit, but it makes it work better in the long run, so it's kind of a necessary evil. They work by doing something called a chelating agent, and basically what happens is they replace 2 of the sodiums with 1 hard ion. So if we look at down here, we have all of these sodium molecules, which are our hard ions. And basically what happens is calcium comes along and it kicks out the 2 sodiums and it bonds right here. And sodium's bad. It affects our ability for our soaps to work properly, our detergents to work properly. So if our sodiums and our calciums are busy, because calcium was one of those ones in the list saying from carbonates, right, from our calcium carbonate in our limestone. Remember me saying that? So now calcium's busy. It can't affect our detergent anymore. It can't affect our cleanliness of it anymore. Well, so you're at the store and you're in the detergent aisle and you have 50 different options, don't you? You have Tide. You have, I actually can't even think of any of the names. I buy mine at Sam's. But you have 50 different options. Some of them are in blue bottles, some of them are green bottles, some of them in pink bottles. They're honestly all the same thing. Basically, the price difference comes from how the packaging, how much money goes into packaging it, and how much money goes into advertising it. So just because you're buying a more expensive brand doesn't mean it's necessarily a better soap. Because a detergent is a detergent is a detergent. It all does the exact same thing. It uses the same basic chemistry. There's really no way to change it to make it any better. So what we can do in some of these things, like in soap, now they add air because bar soaps, if you guys have ever noticed, if you drop it in water, it floats. Well, they didn't used to that, used to sink, but they added air to it to make it float, make it easier to find. They also started adding perfumes to soaps and detergents to make them smell better. They also started adding enzymes. This breaks down proteins because sometimes, like for instance, if you get a chocolate stain on your clothes, well, chocolate is actually a type of protein because chocolate is oftentimes made from dairy, right? So if you put some enzymes in the soap, it'll break down the proteins found in that chocolate stain, which is why we have stain fighters that work a little bit better than detergents do. We also sometimes can add optical brighteners into our clothing, and this makes clothes look brighter. They don't clean it any better, though. So just because we're putting an optical brighter, it's actually like an optical illusion for your eye. So like they used to, white sheets, over time they yellow. And so have anyone ever seen like on TV they'd put like a blue solution in the water when they're washing the white sheets? Well, the blue counteracts the yellow, and so you see bright white, but it's really not that bright white. It's just an optical illusion. It's not like it's really cleaning it any better. The other kind of additive is a bleach. This is an oxidizing agent. Basically, they tear apart your organic molecules. Bleach is a really good cleaning agent, but at the same time, it can be very, very, very bad. So this is why the bleach we buy at the store is usually 5% bleach and the rest of it is water. Because if we had very strong bleach, it would honestly ruin your clothes. Some other detergents that we use in everyday life is shampoo. Basically, same thing with shampoo as soaps and detergents. It's all the same thing. You can add different fragrances, but for the most part, you don't need to spend $20 on shampoo because it's the same thing, same basic chemistry. Toothpaste. Toothpaste is honestly detergent with a little bit of baking soda in it. That's why it suds up in your mouth. So basically, when you're brushing your teeth, you're using detergent, which is kind of gross, right? So your homework is on page 259. It is numbers 1 through 18. There's a picture of how a surfactant works. I like my pictures. So that was a short chapter, right?